So an electric cell. So when we look at an electric cell, I have given here two pictures. The first one is mostly what we use in the chemistry lab, or the understanding comes from the process of electrolysis in chemistry. Whereas the second one is something more commonly that is used in the electronic devices that we have at home. So if you look at the first case and the second case, it's nothing different. It's exactly the same thing. The packaging is different. It's like if you take milk, butter, or any of these food items that are there, might be prepared by the same industry, the same ingredients that are there, but the packaging will be different. Maybe slight, difference in taste here and there. But then the packaging is what makes it different. You cannot, let's say if you are using a camera, you cannot carry around this solution that is there in your camera and tell that I'm going to use this as a cell. No, it's not going to work. So maximum what you will do is you will take a 9-volt battery that is there over here and you'll plug it into your camera for it to work. Or maybe a AA battery, depending on how many batteries are required. So what is the difference between a cell and a battery? So if you look at this, an electric cell here, I've got two terminals, positive, negative, which is there in each and every one of these batteries as well. There is a carbon and zinc electrode. Now the central rod here, the cap that you see will be the carbon. Anything that is surrounding it will be the zinc electrode. Here we have acid. So what happens? In this acid, the process of electrolysis takes place whereby negative charges move towards the carbon electrode and the positive charges move towards the zinc electrode, thereby ensuring that there is going to be movement of charges or production of current. So I can simply write the negative sign here and the positive. So the electrolyte would ionize and we would have the process of electrolysis. But in a battery that we have here, this process wouldn't take place. So it's more of a chemical reaction that takes place at a different level. So what is an electric cell? So an electric cell consists of a source of electrical energy which maintains a continuous flow of charge in the circuit. That means the charge has to flow. So here if you see, for example, I have two small batteries which are connected in the reverse combination. So this is going to be, let's say, plus, minus, plus, minus, which constitutes a battery. That means our understanding should be a battery is going to consist of multiple. Now, if you see, there is one wire that is connected to the bulb, the other wire to a switch, and then back to the battery, which is completing the circuit. So throwing the switch on or off, or switching it on or off will make sure that the bulb glows or not. Now, this is maybe the simplest form of a circuit that we can know, we can draw. But there are also such forms of circuits. Complex. You've got a huge number of cells. You've got a lot of resistances here. Maybe even capacitors can be thrown into the mix, or even let's say semiconductors, diodes, wires, LEDs, all of these things can constitute a complex electric circuit. But there also, the electric cell is the only thing that is there which acts like a source of electrical energy. So let us understand what exactly an electric cell does, what is EMF, what happens when we connect resistors in parallel, cells in series, and what are the, let's say, rules that are there whereby we can say when current will be maximum in a given circuit. So now let us look at EMF of a cell. So when we're looking at EMF, what is the meaning of EMF? So before that, let us look what a cell is. So if I take something like this, if I take two lines which I can put together, now we call this as a cell because this has a positive as well as a negative side that is there. Earlier times, the entire process of defining a cell was done by using a chemical process called as electrolysis, where if we take a container that would be filled with an electrolytic solution, we would insert two rods which would serve as the positive and the negative that is there. So this would be connected. Let's say if we connect this to a bulb, it would glow because one end, if it is positive, negative, the negative ions that are there would get attracted towards the positive end of the rod, and the positive ions would get attracted to the negative end in this electrolytic solution, and then the bulb would glow. So what is EMF defined as? So EMF is defined as the ability of the charge to move in the circuit. To move in the circuit, or we can even call it as the work done. In more physical terms, it is the work done in moving 1 coulomb of charge throughout the circuit that is there. So that is what EMF of a cell is. So for instance, say we can draw a circuit. In general, the resistance that is there is going to be our, it can be the bulb or anything else that we are going to put in this given circuit. So here I'm just going to take some amount of resistance. We can even put a light bulb. A light bulb here will act like a resistor. So this is R, this is V. So the force that is done, or force that is needed for an electron of charge 1 coulomb to go around the entire circuit. Throughout the circuit, that is to complete the track around the circuit, is called as the EMF. Now there are a couple of things that are related to the EMF that we will have to. So EMF is abbreviated as electromotive force. So that means the force that is needed to make the electron move. That is what is EMF. So in general, if you see, the symbol that we are going to use for EMF will be a small e or an epsilon. It can be, you can call this as E, but this is a Greek letter epsilon that we are going to use. Now this is going to be V plus V minus, which is going to be less than 0. That means this is a very small force that the electron feels. It's not saying that if I have a potential difference of 9 volt, the electron is going to feel the entire 9 volt. No. The electron is going to feel the force for which the work is done, that is moving around this circuit. Now, before we proceed any further with a deeper understanding of EMF, an important concept that we have to understand is something that is related to internal resistance. Now, what is the meaning of this? If you see, we have got a capital R in the circuit, which is our external resistance that is there. So an electron that is moving, because of the external resistance, it will have to do extra amount of work to move. But at the same time, within, let's say, the wires of this conductor, before it connects to the resistor, there is going to be movement of electron, and they are going to face the resistance of all the other electrons here. For instance, crossing this potential difference, they are going to face the resistance. So that resistance is the internal resistance of a given circuit. Now in general, when we have done series and parallel connection, we have only looked at the external resistance. We have not considered the internal resistance. So when we are looking at the EMF, an important factor to consider is the small r, or the internal resistance. It has the same unit as that of resistance or external resistance, which we use ohm. So as the electron is going to move through this entire circuit, there is some amount of work that is being done in order to cross this potential, and also in order to overcome the internal resistance along with overcoming of the external resistance that is there. So now we can have a look at our understanding of Ohm's law. So till now, Ohm's law we have taken as V equals IR. And since we have internal resistance, now we have to see how this is modified and how the EMF is going to come into this expression. So what we will do is, capital R will take as the total resistance. We'll write it as R plus small r. We'll take this as RT. And the potential difference basically is going to be the EMF here in this case, which we write it as capital E, small e, or epsilon. Because we know that epsilon is V plus V minus. That is the total potential that is there in the entire circuit that is experienced by the electron. Now let us go ahead and substitute. So we are not going to write V plus and V minus, we are simply going to write it as E or epsilon. is equal to I of capital R plus small r, if I've taken this as the total resistance. So current is going to be nothing but E by R plus R. So the current that is there is the EMF by total resistance. But our actual Ohm's law was only V is equal to IR. We didn't have total resistance or EMF in the picture here. So what we will do here, we are going to substitute the value of I in terms of the EMF by the total resistance. So I will get the total potential difference that can be established between the two electrodes, let's say positive and negative electrode, is going to be nothing but R times epsilon by R plus R, or V is equal to epsilon divided by 1 plus small r by capital R. So the final expression is V is equal to epsilon divided by 1 plus small r by capital R. Now the understanding is small r is never equal to 0. You cannot take less than 0. We don't have negative resistance. But small r is negative, never 0. That is, there is always going to be internal resistance. So that would mean that V is less than epsilon. Now this V, we call it as the terminal potential difference, or the terminal voltage. This is in common terms, but V is generally called as the terminal potential difference that is there. So if I don't have internal resistance, when R is equal to 0, then V is equal to E. That is, the terminal potential difference will be equal to the EMF of the circuit that is there. So now, since I've got this as equal, and we know that they are not one and the same, let us look at the difference between EMF and potential difference. So the EMF of a cell is nothing but the maximum potential difference between two electrodes of a cell when the cell is in open circuit. Now the understanding here is the amount of work that is done for the charge to move around the entire circuit once, when we call it as an open circuit. Whereas potential difference is the difference between 2 points, between potential between these 2 points in a closed circuit. That means the amount of work that is done in moving between 2 points in a closed circuit, or in any given circuit that is there, is the potential difference. The EMF is independent of resistance of the circuit and depends on the nature of the electrodes and electrode. That means it doesn't look at the overall resistance. It is bothered with the internal resistance only. Whereas potential difference depends on the resistance between 2 points in a circuit and the current flowing through it. That means we are looking at the external resistance in a potential difference that is there. EMF is used for source of current, whereas potential difference can be measured between any 2 points in a circuit. Now EMF of a cell is nothing but the cause because of which electrons will start moving. There is a force which causes the electrons to be in motion. Whereas potential difference is an effect that is there, something that we can feel that is there. Now, since EMF of a cell is used for the source of the current, it does not depend on the current that is drawn from the circuit that is there or from the cell. Whereas in the potential difference, it basically depends on the current that is drawn throughout the circuit from the cell. So from the cell, the current passes through the circuit, which is drawn using potential difference. Now, just like how we had, let's say, resistors in series and parallel, so also can we have cells in series and parallel. And we have to look at how we are going to solve that. So first, let us take a series connection. So let us draw our circuit. So this is our circuit. We'll have some spaces for drawing our cells. So instead of resistance, now we are going to draw, let's say, 2, 3 cells, or we can just do it for n number of cells that are there. This is the external resistance in the circuit. So if I have a cell here, another cell here, let's say we end up having n cells that are there. with one external resistance. So this is going to have E and R, electromotive force and internal resistance, and this is going to be my external resistance. Now in order to simplify this, let us look at a simple set of two cells only. So if I take two cells or a simple set of it, let's see what we get. I'm going to have positive, negative, positive, negative. So I can take this point as point A, this point as point B, the central point, this point as point C, and there's current that is going to pass. Now why I have taken this is I can calculate the potential difference between point A and B, between point A and C, since we are having two cells. So their EMFs are E1 and E2 with internal resistance R1 and R2. So VA, VB and VC are potentials at A, B and C, points A, B, C. Now the convention that we have to use here is we've got positive, negative. So positive would mean an increase or rise in the potential, and negative would mean a decrease in potential that is there. So let us go ahead and look at it. So first let us look at VA. So VAB, potential between A and B, will be nothing but VA minus VB, which we can write it in the following way, that is minus of plus IR1. We can write this as E or epsilon, both are one and the same. Similarly, VBC is going to be nothing but VB minus VC, which is going to be minus E2 plus IR. Now, total, that is VAC is going to be nothing but VAB plus VBC. That will give us VAC is equal to minus E1 plus IR1 minus E2 plus IR2, which we can write it as minus of E1 plus E2 plus I of R1 plus R2. Or we can write the same thing as VCA is going to be equal to E1 plus E2 minus I of R1 plus R2. So I have only changed the potential. So from A to C when I am measuring, I will have minus E1 plus E2. Whereas from C to A when I am measuring, it becomes minus I of R1 plus R2. So here I can simply write E1 plus E2 as the EMF effective that is there, and R1 plus R2 is the resistance effective, or effective resistance and effective EMF. So if I have N cells that are there, then E effective is going to be nothing but E1 plus E2 plus etc. up till En, and R effective is going to be R1 plus R2 plus etc. plus Rn. Now this I can write it as summation Ei, I going from 1 to N. Similarly summation here Ri, I going from 1 to N. So that means the current that is there, we had it as E by R plus R, which is going to be in terms of sigma now. So I can simply write this as sigma I equals 1 to N Ei divided by R plus sigma I is equal to 1 to N Ri. So this is for N cells that are connected in series. Now let us connect the same set in parallel and let us see what happens. So a parallel circuit is a box circuit that we have. So we have our EMFs here. So this is one cell that is there. This is another cell. So here I will have E1 R1. This is going to be E2 R2, I have the current that is flowing towards this side. This is how the current flow is. So this is point B, this is point A. Now, we know that since it is a parallel circuit, the current is going to split in this form, I1 plus I2. I'm not giving exact numbers, I'm just telling it splits as I1 and I2. So since it is going to split, we are going to have two potentials at point A and at point B. At A and B. So the total potential V will be nothing but VA minus VB, which we get it as E1 minus IR1, or our current is going to be I1 is equal to V minus E1 by R1, that is minus I. So I is going to be equal to, or I1 is going to be equal to E1 minus V by R1. This is for the first cell. Now if you see, point A and B are even connected to the second cell. So I can simply write I2 is equal to E2 minus V by R2 for the second cell. So this is when potential VA and VB are present for this parallel circuit. Now let us substitute this in the total current. I equals I1 plus I2. So I will get I is equal to E1 minus V by R1 plus E2 minus V by R2. So let us take the LCM and solve. I will have E1 R2 minus V R2 plus E2 R1 minus V R1 whole divided by R1 R2. Now we can separate them out. I will have E1 R2 plus E2 R1 in one group minus V of R1 plus R2 whole divided by R1 R2. Now this is equal to I. So let's take R1 R2 to the other side. So I will get I times R1 R2 is equal to E2 R1 plus E1 R2 minus V of R1 plus R2, or V of R1 plus R2 is equal to E2 R1 plus E1 R2 minus I R1 R2. V is equal to E2 R1 plus E1 R2 by R1 plus R2 minus I R1 R2 by R1 plus R2, that is there. So this we have again come back to our expression V is equal to E minus I R. So this we can write it like this. That is, if I write the expression again, E2 R1 by R1 plus R2 minus I of R1 R2 by R1 plus R2. E effective is nothing but, in this case, E equivalent by R equivalent, which is equal to E1 by R1 plus E2 by R2, and R effective is going to be 1 by R equivalent, which is nothing but 1 by R1 plus 1 by R2. So if we have, let's say, n number of cells that are connected in parallel, cells, then we can have a look at the EMF. So we can write it as E equivalent by R equivalent is equal to summation I is equal to 1 to n EI by RI, and 1 by R equivalent can be written as summation I is equal to 1 to n 1 by Ri. So our expression will become V is equal to sigma EI by Ri, I equals 1 to n, minus I times sigma I is equal to 1 to n, 1 by Ri. So this is the general form for writing if you have n cells in parallel, that is there. So right now we have seen two connections for the cells that are there. The first one is the series connection. The other one is the parallel connection. Now, when we look at this, there are always chances of the parallel connection sometimes being done wrongly. So in that case, what do we do? Or how do we find what is the effective EMF of the cell? So for that, what we will do is, let's say we will take a particular series of parallel EMFs that are there. Let's say we'll take cells which are parallel to each other. We can take something like this. So I'm going to have a set of roughly 6 cells. So yes, so these are 6 cells that I have, or 6 different circuit lines that are there. I'm just going to put in my cells here. Okay, so I will have positive, negative, positive, negative. Now what we will do is, we'll just make sure that some of our cells are wrongly connected. So this is one. Let's say this is the second one. This is the third one. So third one, what I have done, the third and the fourth, possibly I have connected it in the reverse order as compared to the other cells that are there. So I have finished this. Now in this case, if we see, we know that even if I connect this to an external resistance that is there, this entire thing, if I connect it to a net external resistance, there is no way that my circuit is going to function in the intended way, because we have got two cells that are there mixed up. So it is these two who are mixed up. So this and this. Whereas all the others are proper. So what we can do is, we can simply write this as, let's say, the first one. Just for simplicity's sake, I'll just take this as 1, 2, and let's say 3, 4, 5, 6. This is capital R, the resistance that is there. Now, 3 and 4 are connected wrongly or incorrectly in the circuit. Now, since they are corrected, let's say connected incorrectly in the circuit, what we can do is, we have to calculate what is the E effective. So the E effective in this case can simply be taken like this: sigma EI by Ri minus sigma EI by, or sorry, EJ by Rj, whole divided by sigma of 1 by Ri plus 1 by Rj. So what I've done, I've taken both into consideration. So if I, let's say, expand and write, so E effective can be written as, so for this circuit I can write it as E1 by R1 plus E2 by R2 minus E3 by R3 minus E4 by R4 plus E5 by R5 plus E6 by R6 divided by 1 by R1 plus 1 by R2 plus 1 by R3 plus 1 by R4 plus 1 by R5 plus 1 by R6, since I have taken 6 cells that are there. And similarly, I can figure out what is the R effective is nothing but 1 divided by this entire term that is there. That is 1 by R1 plus 1 by R2 plus 1 by R3 plus 1 by R4 plus 1 by R5 and plus 1 by R6. So now let us look at the mixed grouping of cells. We have already seen what is the effective EMF and the effective resistance. So the effective EMF is E effective is equal to, we had E1 by R1 plus E2 by R2 plus etc. up till En by Rn whole divided by 1 by R1 plus 1 by R2 plus etc. plus 1 by Rn. Now, if we consider this diagram here where I've got multiple cells as a mixed grouping in both series and parallel, that is, we've got multiple cells in series which are connected in parallel. So you can see that I've put dotted lines here, which mean that there are many more series connections within this entire parallel. So I can take this entire ensemble or group of parallel connections that are there. That's why it says m rows of n cells each. So there are n cells with m. So we have m rows of n cells. Now these n cells are in series and these m rows suggest a parallel combination that is there. Now let us see whether we can find a general formula for this which we can use later on for solving problems in case of competitive exams. So since we have n cells in series, we can look at the total EMF that is there of these cells. So total EMF in series combination, this we get it as equal to n times capital. Now, since all the series are connected as parallel, so it is first a series connection, then parallel connection. So the total EMF, if I take of the whole cell or the whole circuit, is going to be equal to n times capital E. So it is going to remain the same. That is, this entire combination will be equal to n times E. Now, for this kind of a cell, let us look at what is the total internal resistance that is there. Now, the total internal resistance for this is going to be n times small r. So, total internal resistance is equal to n times small r. Now, for this kind of a circuit, we can see that we always have a parallel combination of the external resistance. So, if I take R1 as my external resistance, then since it is in a parallel combination, we can simply write it like this. 1 by R1 is equal to 1 by NR, that is for the first line of the series, plus 1 by NR, second line of the series, plus so on up till it reaches M terms. That means the last term is going to be nothing but M times 1 by NR. So I can write it as M by NR. So this is going to be my resistance that is there, or that is 1 by R1, or my R1 is going to be nothing but NR by M. So we have already seen the total EMF, the total internal resistance. Now let us look at the total external resistance that is there. So the total external resistance that is there is going to be equal to capital R, which I'm going to take it as N times R by M plus capital R that is there. Now this is as per what is given in our diagram. So now we can go ahead and calculate what is the current. So current is equal to I is equal to, according to Ohm's law, we will have V by R, but in this case, we can write it as N times E by R. That is nothing but NR by M plus capital R. So we'll just try and simplify this. So I will have NE divided by N small r plus M capital R by M. So we will get the current to be MNE by NR plus M capital R. Now for our current to be maximum, the denominator should be minimum. So that means if I have 1 by a small number, I will get is equal to a large number. So for instance, if I take 1 by 0.5, we will end up getting the value as 2, which is a large number compared to the denominator. So if I has to be maximum, then NR plus M capital R should be minimum. Now, in order to get this as minimum, what we can do is we can try and find out what is this value and from where does it come. So we can go ahead and look at the expression that we have now, a plus b whole square, a minus b whole square. We can arrive at this from somewhere from that kind of an expression. So we can simply write it in this particular format. Since we know square roots and other things, n small r plus m capital R is equal to root of n small r minus root of m capital R the whole square plus 2 times root of mn small r capital R. Now according to our previous statement, for n small r plus m capital R to be minimum, our value of root of nr minus root of mr the whole square should be a minimum value. Now if this has to be minimum, that means we can just get rid of the square root. So minimum means we know the value should be equal to 0. So let's write it. Root of n small r minus root of m capital R whole square is equal to 0. Root of nr minus root of mr is equal to 0. Root of nr is equal to root of mr. Let's square both sides. Squaring both sides we'll get nr is equal to mr, or capital R is equal to nr by m. But what is this nr by m? It is the internal resistance of the whole battery. That is, we had series cells or batteries which were in series, then in parallel. So this entire system that was there constituted to one huge cell. So this nr by m is the internal resistance of that whole battery. So let us have a look. We had the current expression which was given by I is equal to n times E by nr by m plus capital R. So when we substitute this value as R that we just found, I will get current as nothing but NE by 2R. So here we can see that the current is maximum. So depending on the value of R, I will end up getting maximum value of current. So we can conclude that in a mixed grouping, the current in the external circuit will be maximum when internal resistance of the battery is equal to the external resistance in the circuit. So So in this circuit, if I see, I have got m cells or m rows that are there with n cells. Now we can consider this entire thing as one huge battery, because what happens for each row, we find NE to be the total EMF, which is going to be the same for all the series, right? So the total EMF that is there in the cell is going to be NE, for which we figured out that our external resistance was nothing but N times internal resistance by the total number of rows that are there. So only if the external resistance is equal to internal resistance of this full thing, which acts like a big battery. So this circuit, I can simply simplify it and write it like this. So it is one huge battery and one resistance R. So when these two are equal, the current will be maximum, because if you see what is the current expression here, I is equal to NE by 2R. So for huge value of resistance, 1 by R is going to be a small number. That means automatically I is going to increase. So as resistance would decrease, current would also increase. We can take it in that way. Suppose NE is constant. So let us look at a few cases. Now, in the first case, I can take my external resistance to be greater than the effective resistance that is there. That means capital R will be greater than small r by N. So how many ever internal resistances are there, the effective one is the capital R, external resistance is going to be greater. So in this case, what happens to the current? I is nothing but NE by N capital R, which I will end up getting it as E by capital R. This implies that the current that is there is due to a single cell. Now, on the other hand, if we take the external resistance to be less than the total internal resistance that are there, then what do we get? We will get I is equal to N times E by capital R, which means it is nothing N times current due to one cell. So from this we can understand that the parallel grouping that is there, or parallel arrangement of cells, is beneficial only when capital R is much less than the internal resistance that is there, is R by N. Next, let us have a look at the mixed grouping that is there. Now, whenever we tell mixed grouping, either in resistors or let's say in cells or even in capacitors, mixed grouping basically means we have both series and parallel. Now, in these cases, what is going to happen to the total EMF and the effective resistance that we have to calculate? So for that, let us start off with a circuit diagram. So let us look at this mixed grouping, both series and parallel. We have got, we can have, let's say, n rows that are there, or we can have m rows and n columns as a standard notation that we have. So I'll write m rows and n columns. Now the idea here is to solve this, let's say, series and parallel combination of cells that are there. The working is similar. So what we will do is, in this case, we'll have to figure out what exactly to do. Previously, let's say in resistors, what we did, all the parallels we added and then we added in series. But here if you see, the cells themselves are in series and then they are in parallel. So we will have to make sure that we find a circuit which has something like this. So I get the series combination and then this is connected to an external resistance. So I combine the series in each row, and then for whatever effective resistance we are going to get, or effective in this case cell, that is the EMF and the effective resistance we are going to get, we will make sure that they are added parallel. So for this we can go ahead and write what the current is going to be. So in the first case, the current is going to be nothing but MNE divided N times capital R plus M times small r. So this is a straightforward substitution for this kind of cases, where the total current will be nothing but number of rows into number of columns into the EMF divided by number of columns that are there into R plus number of rows into M, or R in this case. So when I tell columns, basically what I'm trying to tell is M is nothing but number of cells that are there. So if you look at it vertically downward, these are columns. But as such, M will be the number of cells in this row, and N will give us the count of the total number of rows that are there for this kind of a mixed grouping circuit. The next thing that we have to understand is the condition for maximum current, because now this is going to have a lot of resistances that are there. So what will be the condition for maximum current? So in that case, we are just going to take the external resistance capital R is equal to internal resistance, that is small r, total. So I can have capital R MR by N. So the maximum current that is there, I max, can be found to be MNE whole divided by square root of MNR times small r into 1 by 2. So we can use these ready reckoner formulas that are there when we have, let's say, objective types questions or competitive based questions to answer. We don't have to derive the entire thing, but straightforward we can use this. Now these we have arrived at using the relations that we have already found. So this is maximum current. So if we have maximum current, we can calculate maximum power also. So max power will be equal to nothing but I square R, which is equal to E divided by capital R plus small r, the whole square into capital. So the underlying condition for Pmax, or the maximum power, is R external is equal to R internal. So what happens here, I'm just going to get this as E square by 2R the whole square times R. So the power is going to be what? So Pmax now is going to be nothing but E square by 4R square times R, which is nothing but E square by 4R, or Pmax, this is in terms of external, I can write it in terms of internal also, E square by 4 small r. This is external resistance, small r is internal resistance that is there. So in this circuit here that you can see, I have got a cell, a voltmeter or a multimeter that is used to measure the potential difference, one of the functions of a multimeter. Also an external resistance is there. Now in this circuit we are just going to try and figure out what exactly happens to the EMF of a cell, or what happens to the cell when we use an external resistance. So here you can see that we've got the cell, which is the black and white right at the top. So this is our cell that is there, which is a 9-volt cell. Now in this multimeter you can see that it is reading 8.911 volt. It is not reading the exact 9 volt that we want. Why is it not reading 9 volt but 8.911 volt? Now it is very simple when you look at it, because we have the idea of internal resistance that is present in the cell. So if we didn't look at internal resistance, that is a small r is equal to 0, then we would actually be looking at a 9 volt cell which would supply current meant for 9 volt. Now since we have taken internal resistance also into consideration, the entire voltage would drop a little bit to give us 8.911 volt. So we can go ahead and consider our cell that is there to be a perfect cell. So when we tell it is a perfect cell, our understanding is that it is going to supply current meant up, and at the same time it is going to go on ahead and we are going to get a certain potential difference. Now in this potential difference that is there measured, we are keeping in mind that there is an internal resistance of the cell also taken into consideration. So whatever current it is going to draw, now we can make sure that we have a limitation on that, because we have an external resistance which is the maximum that I can set for the simulation, which is 100 ohms. 100.00 ohms is the maximum external resistance that is set for this particular circuit that is there. Now the reason why this let's say voltmeter is reading 8.911 volts and not 9 volts is because I have kept the internal resistance of this cell as one internal resistance. But in the real case, we have to look at internal resistance, and that is why I have made sure that there is some internal resistance, a minimum internal resistance of 1 ohm, whereas we have an external resistance of 100 ohm. So the external resistance is greater than the internal resistance that is there. Also, if we see for this kind of a circuit, we do not have a lot of current. The current is only 0.09 ampere that is flowing, or we can take it as 90 milliampere is the current that is flowing through this. It is a very small current. So what we can do is we can reduce the external resistance so that there is maximum current flow that is there in this circuit. So we have seen the expression for maximum current flow in the previous slides that are there. So using that idea that we already have, we will go ahead and reduce the resistance, the external resistance that is there, and see what happens. So as the resistance keeps on decreasing, or when we have increase in the current, the EMF or the potential difference that is there for this particular cell will keep on decreasing. So this is something that we are going to manually do. So now let us go ahead and decrease the resistance and see what happens to the potential difference that is there. So let us begin. So from 100 ohms, I will slowly start decreasing. You can see that there's a decrease even in the EMF. So somewhere when I come to 60 volts, it's 8.7 and so on. It is decreasing. So you can see that the moment I arrive at, so you can see that external resistance has decreased to 4.71 ohm. From 100 ohms, we've reduced it to 4.71 ohm. So roughly around 95 change, we have reduced it. Now at the same time, if you look at the current, which was 0.09, now it has become 1.58 ampere. The current has increased in the entire circuit. Similarly, if you look at the potential difference, it has become 7.42 from 8.9. So our ideal case, it was a 9 volt cell that we took. And in the real case, we found it to be 8.9 volt because of the internal resistance that is there. Now you can see that as the external resistance is decreasing, the potential difference keeps on decreasing. So we finally stop at 7.42 as the potential difference for an external resistance of 4.71 ohm and a current of 1.58 ampere. So what is the understanding? The understanding is the internal resistance of the cell is squeezing in or is absorbing or taking a lot more potential that is there. So that is why the potential difference keeps on decreasing. So we had a case where capital R was greater than small r, and now we have reduced R to a smaller value, that is the external resistance to a smaller value, to facilitate maximum flow of current. So now what we will do is we will go ahead and make sure that we are looking at an ideal cell that is there. So we will just go ahead and remove the internal resistance that is there and make sure that it becomes 0. So we have removed the internal resistance, and what we will do is right now we will add an external resistance. So here is the external resistance, and since we can change the resistances, internal resistance we kept it as 1 ohm, we will do the same. So I have an external resistor here with a resistance of 1 ohm. Now I will go ahead and try and find out what is the potential difference. So I take the probe a little away, so you can see it is 7.42. Internal resistance that is there. Now that internal resistance was hidden within the cell, which we didn't see earlier. So right now we are going to bring that into the picture. So I will go ahead and take my red probe and put it exactly in front of the resistance, or in between the cell and the resistance that is there. So now we can read what is the potential difference that is there in this meter. You can ignore the negative sign, but our understanding is what it is. So now we will do the same thing as last time. We will keep on decreasing the external resistance so as to see what happens to the EMF of the internal resistance that is there. So let's keep on decreasing. We can see that the current increases. At the same time, the resistor that is there, you can see what is happening. It is building its own potential. So somewhere around, let's say 1.58, 4.71 ohm, the resistance that is there is 4.7 ohm external, 1 ohm internal resistance, for which we get 1.576 volt as the potential difference across the internal resistor. Well, so this is what we get. Now let us go ahead and see what else we can do. Now why is it negative? Is because the positive negative is right left switch, that's it. As in the sense we have not taken the exact, the internal resistance should be within the cell, right? So since we have put it in front of the cell, we are going to get it like that. Now what we will do is we'll remove this piece of wire here between the external resistance and the cell, and we will see what is the potential difference. So if it is exact, we should get 9 volt, and voila, we have 9 volts here. So here when you go ahead and disconnect, let's say the circuit that is there, and then you try to measure the potential difference that is there, that is the EMF of this particular circuit. So you can see that the moment I removed the wire that was connecting the external resistance, so this is an open circuit, and I tried to measure the potential difference, I found it to be exact 9 volt as that case of an ideal battery. So this is the understanding of EMF.